Hello guys, in this video we are going to be looking at equation under rate of reactions. This video is specifically for students who are preparing for the medical entrance examination. So if you're one of them, then this video is for you specifically. Alright, because the question we are going to be solving is kind of your past examination question. Okay, so first of all, I am not a chemist. I don't love chemistry, but I do love physical chemistry because there is a lot of mathematics that is involved there, and especially in this topic called rates of reactions. So it's one of my best topics in chemistry because there is a lot of mathematical analysis that is always done in that topic. Okay, so there are some key things I would like us to note. First of all, I would like us to know what we call initial speed of a reaction. Initial speed of a reaction. Alright, what's the initial speed of a reaction? The initial speed of a reaction is simply the rate of that reaction. Okay, the initial rate of the reaction. That is, we know that the rate of any chemical reaction is equal to the rate constant times the product of the concentration of the reactants raised to their partial orders. Alright, so for example, if I give you a reaction where we have A plus B react to give us C. Now let's take a reversible reaction. So we have A plus B reacting to give us C plus D. Okay, then we are going to see that the rate of this chemical reaction is a rate constant K times the concentration of the reactants raised to their partial orders. So the first reactant is A. That representation means the concentration of A raised to the power, let's just say the partial order of A is small a, and concentration of B raised to the power, the partial order of B is small b. Now these partial orders A and B are not the coefficients here. Let's just say if this is X and this is Y and this is Z and this is maybe W. Okay, so our A and small a and small b are not necessarily X and Y. In fact, they are never X and Y. They are X and Y provided this particular equation is a rate determining step. But if this is the equation itself, the original equation for the chemical reaction, then the partial orders of the reactants are not the stoichiometric coefficients of those reactants in the chemical equation. Okay, now small a is called the partial order of the reactant A, and small b is called the partial order of the reactant B. And we see that in this case, when we are dealing with the rate, we just deal with the reactants. The product have nothing to do here. Alright, to make things convenient for us, we are just going to let me just consider just a situation where we have just one reactant. Okay, so maybe consider the reaction below. Alright, so let's just say a reactant A undergoes maybe a certain reaction. So the reactant A undergoes a certain reaction to give us a reactant B. Alright, so this is our, let's just say, okay, yeah, this is our chemical equation. Now what is the rate of this chemical equation? The rate of the chemical equation, that's the rate of that equation, is equal to the rate constant times the concentration of the reactant raised to its partial order. Now in this case, since we have only one reactant, then we can conclude that the total order or the order of this reaction is just equal to the partial order of that reactant, which is n. In this case, we have that small a is the partial order of reactant A and small b is the partial order of reactant B. So the total order of the reaction is A plus B. Alright, now in this case, you clearly see that the total order is still n because you have just one reactant, so the total order is n. Now we are going to get a relationship between the concentration of this particular reactant with respect to time, provided maybe it is zero order, first order, second order, third order, and so on and so forth. Okay, now we should also note that the rate of a chemical reaction is simply the change in the concentration of the reactants over time. So the rate of a chemical reaction is also the change in the concentration of the reactant with respect to time. Alright, and since the concentration of the reactants will actually be decreasing, then we put a negative sign in front of it. So this negative sign here represents that this reactant, that's the concentration of the reactant, is actually decreasing over time. Alright, so it's kind of a decay, let me put it that way. Alright, so let's now analyze the first case. Let's take case 1. In our case 1, we are going to say, okay, our reaction order, so n is equal to 0. That is, the reaction is 0 order. That is, the reaction is 0 order. Alright, if the reaction is 0 order, what do we have? We have that the rate of the chemical reaction will be equal to the rate constant times the concentration of the reactant raised to the power 0. And we know that since the concentration of the reactant cannot be 0 initially, then when you raise it to the power 0, this one is going to give us 1. So at the end of the day, I'm going to replace the rate with this identity here. So we have this, sorry about that, we have this to be equal to k, because this is going to give us 1. That's this is going to give us 1. Alright, now from there, what do we have? We can find our negative d of the concentration of the reactant will give us k dt. Now things start becoming very interesting. Mathematics is now involved. This is a first order differential equation where we can separate variables and integrate. So that is why I love it. So I can now integrate both sides. I put a negative outside, dA, and then here I have k, and then I integrate dt. Okay, remember that k is called the rate constant. Okay, so from here, what do we have at the end of the day? We have that negative d of the constant. In fact, if I integrate dA, I'm just going to get a. Okay, I'm going to specify that it's at time t equal to kt plus a constant of integration. So you see that we have two constants. We have the rate constant, which is k, and then we have the constant of integration, which is c. So you're always going to be given initial conditions to be able to find the rate constant and the constant of integration. For example, I will tell you that maybe initially the concentration of the reactant is equal to A0. Okay, so initially we have that the concentration of the reactant, that's the concentration of the reactant at t equal to 0 is equal to this. Okay, so from there we can be able to actually find, because you always be given, maybe you might be given this value. Okay, so from here we just need to replace t to be 0 here. This term is going to disappear, so our constant of integration will just give us negative times the initial concentration of the reactant. It therefore means that I just need to copy everything here, and then I paste here, and then I replace this man here with negative of the initial concentration, that is with this. Alright, so if you divide all through by this negative sign, this becomes negative, and then this becomes positive. You see that if you draw a graph of the concentration of the reactant against time taken, what are you going to have? You're going to have a straight line, okay, where the intercept is going to be what? The maximum, the initial concentration, which is actually the maximum concentration, and then the slope is going to be negative k. But since our rate constant is positive, then negative of it becomes negative, so it's going to be a negative slope. Alright, so how is a graph going to look like? So we can just plot our graph. So we have you have the vertical axis, that's the vertical axis. We have the horizontal axis, that is the horizontal axis. Then Now we are plotting a graph of the concentration of the reactants over time. So we have the concentration of the reactant with respect to time. So give me a few minutes, let me do this fast so we proceed. Alright, so this is what is going to be on my vertical axis, okay, and then what about on my horizontal axis? My horizontal axis is just going to be the time taken. So this is my horizontal axis, the time. You can just put a unit. Okay, now we have seen that you have something like y equal to mx plus c. So this the slope is negative, so it's going to be in this. Here is going to be the orientation. We know when the slope is negative, then we have that here is the orientation of the graph, right? So that is it. So we have something like this. Now let me just put it in a different coloration. So we have something like that. Now when time is equal to 0, the concentration is actually this value here. That is when time is equal to 0, and that value there simply is the initial concentration, which is concentration at t equal to 0. That is the value. Now the concentration keeps on decreasing with respect to time. As time is increasing and going towards the right, the concentration is rather decreasing. Okay, so maybe when the concentration is 0, then time has then maybe you have a certain time. That is when this concentration here is, when this concentration here is 0, we have that the time taken for the concentration to be 0, you can find it, okay, and then you just mark that time here. All right, so that is it for the graph of the concentration of a reactant for a first order reaction. That is it. So K is our rate constant. You can be given some other initial conditions to be able to get that rate constant, because we already know how to get the constant of integration using the initial condition that concerns the initial concentration of the reactant. All right, now let us go now to a situation where, let us go to a scenario. So our case 1 was when the reaction is 0 order. Now let us look at when the reaction is first order. What happens? How do we relate the rate of the chemical reaction? How do we relate the rate of the chemical reaction with its concentration, with the concentration of the reactant, as well as the concentration with time? Okay, so let's proceed. Hope this thing is not boring, eh? Okay, so our case 2 is when our n is equal to 1. When n is equal to 1, the reaction is said to be first order. Okay, and when the reaction is first order, what is the rate of that reaction? The rate is equal to the rate constant times the concentration of our reactant raised to the power 1. Okay, now from here, what do we see? We know that this is the definition of the rate, equated to K times the concentration of the reactant. A first order differential equation, very nice. We can separate variables, right? So we have dA by A is equal to negative K dt. So if we integrate both sides, what are we going to get? We integrate d of the concentration divided by the concentration equal to negative K integral of dt. Alright, so let me just put this up here. Okay, so this means that now if I integrate dA over A, I'm just going to get ln A, ln of the magnitude of A, but the concentration is always positive, and I'm going to equate it to negative KT plus a constant of integration. Okay, so I'm going to specify that this concentration here is at time t, maybe minutes, seconds, but at time t. Alright, so from there now, how do we get a concentration? We just need to take E on both sides. So I need to take E raised to the power the ln of the concentration of A at time t, and I equate it to E raised to the power negative KT plus C. Now what does this mean? We know that E raised to the power the ln of something is just that thing. So we have the concentration at time t. Now we can use the laws of indices here. It will be e to the negative kt times e to the power c. But we know that e is a constant and c is also a constant. Therefore, e to the power c automatically is a constant. Alright, so from there, what do we get? We get that the concentration at time t is equal to, now this guy here is e to the power c. I'm just going to call it a constant. Maybe I can call it lambda, or let's just say maybe alpha. Okay, then e raised to the power negative kt. So that is it. So you see that it is actually an exponential graph which is decreasing because the power of the exponential is negative. So you see, if we plot the graph of the concentration against time, it's going to kind of be a decay curve, right? It's going to be a decay curve. Okay, in fact, if we want to find alpha, let us find alpha. Now, how do we do to find alpha? So let's use our initial condition. Initially, we have that the concentration of our reactant, that is at t equal to 0, is just equal to this concentration. Okay, so it therefore means that I'm going to come here to my previous equation. I'm going to replace this with this concentration, and replacing it there, I'm going to have alpha, and then I'm going to replace t here with 0. So the power becomes 0 and e to the power 0 is 1. Therefore, alpha is the initial concentration. So what do we conclude? I believe you have seen this once upon a time in radioactivity, the decay curve. So this will be equal to, I'm just going to replace alpha with this concentration. So we have the concentration at time t is the initial concentration times e raised to the power negative t, negative kt. Yes, that is it. Now, how then can we find k? Okay, so we are going to introduce now what we call the half-life. Alright, that's a half-life, the time taken for the initial concentration to decrease to half of its original value. So when t is equal to t half, okay, when t is equal to t half, we have that the concentration will be equal to the initial concentration, that's the initial concentration, divided by 2. Now, what does this mean? It therefore means that from there we can get the value of k. Alright, we can get the value of k. So from here, I'm going to replace this man here with the initial concentration divided by 2. I'm going to equate it to everything here, and I'm going to replace the t there with t half. So I'm going to replace this t here with t half. That's the half-life actually. Alright, so let's just say, okay, let's just call it capital T. Let's just call it capital T. Sorry about that. Let us call it capital T. Alright, so from there now, what do we have? So I'm going to call it here capital T. From there, what do we have? We see that this concentration, which is here, cancels with this concentration. Now, having that in mind, on the left hand side we are going to be left with half. On the right hand side we are going to be left with e raised to the power negative kt. Negative kt. Now we can take ln on both sides. Okay, since we need k, we have ln of half equal to, if I take the ln of e to the negative kt, I'm just going to get negative k, negative kt. So from there, what do we have? The ln of half is the same as the ln of 2 to the negative 1. Alright, now the ln of 2 to the power negative 1 is the same as negative the ln of 2. So I have negative the ln of 2 is equal to negative kt. So what can we conclude? We can conclude that our k is equal to ln 2 divided by t, and our t there is actually t half. So we have ln 2 divided by t. Alright, exactly. So you have seen that if you are dealing with decay curve, you always have a0 e to the negative lambda t, where lambda is ln 2 on t half. The same story here. So that is it for when it is first order. Now, how does the graph looks like? It's actually a decay curve. Okay, So I'm just going to do a little sketch. Oh, sorry about that. Let me do back an expansion so you can see. Okay, so in this time around, it is not a line again. All right, it's not a line again, it's actually a decay curve. So as time progresses, you begin from the maximum and then you start decreasing. As time progresses, you start decreasing. That is it. So here is it, where your initial is actually your maximum concentration, and we already know how we can get your half-life. So that is it. So there's a graph of concentration against time for a first order reaction. Okay, finally we are going to end with second order reactions, and then now we are going to solve that particular question, because that particular question was talking about second order reactions. So we are going to analyze it perfectly well. Okay, all right, so let's now go to the last, which is second order reaction. So our case theory is n equal to 2, then it is second order. That is second order reactions. Okay, now what do we know about our rate? Our rate is equal to the concentration, the rate constant times the concentration. Now it's going to raise to the power 2. So from there, than to be doing everything, in fact we are just going to replace this with negative d of the concentration of A with respect to time, and we equate it to k times the concentration all squared. We just separate variables and integrate normally as mathematics students. So negative d, I'm just going to divide by the negative, so dA divided by the concentration squared is equal to negative k dt. If I integrate both sides, okay, so I'm going to be integrating, I'm just going to write this as this to the power negative 2, so that we can easily integrate it, dA, and here we have negative k integral of dt. Okay, so from here now, if we integrate this, we just have negative 1 over the concentration at time t. Here we have negative kt plus a constant of integration. So here's a relationship between them. So if I plot a graph of 1 over the concentration, in fact let's divide all through by this negative. Negative goes, here becomes positive, and here becomes negative. Alright, so if I plot a graph of 1 over the concentration against time, I'm going to get a straight line graph. But if I'm plotting a graph of the concentration against time, it's not going to be a straight line. Alright, it's not going to be a straight line. Okay, so it's going to stress me a little bit to plot a graph, so I think we are going to end here for the analysis of second order. But we know that here is a relationship that relates the concentration of the reactants with time and the rate constant, as well as the constant of integration that we can find. That is actually the constant of integration is always equal to the initial concentration, as we know, because when t is equal to 0, we just replace this one with the initial concentration. Or in this case, it's going to be 1 over the initial concentration. Yes, kind of 1 over the initial concentration. Yes, that's what we are going to have. And here is going to be positive now. Yes, all right. Okay, so now let us go to the question we have in mind here. So this question was sent to one of the groups, and because I love this part of chemistry, I took it as a challenge to solve the equation. Okay, so the equation I cannot remember well, that's the wordings, but we had a reaction where ethanoic acid reacted with sodium hydroxide, and the results, I think it was a reversible reaction. we reacted with sodium hydroxide and we had sodium ethanoate, so sodium ethanoate and water. All right, now we're being told that the reaction, so things to note. The first thing is that, so first, the initial concentration of the reactant, which is sodium ethanoate, so the ethanoic acid, was equal to 0.01 molar. Now the next thing was that the reaction is second order alkaline hydrolysis. Hydrolysis. This just to tell us that sodium hydroxide is not actually a reactant, okay, because alkaline hydrolysis is just saying that this is an alkaline medium, okay, so this is the only reactant. All right, now the next thing was that the time taken, the time taken for half of the reactant to be consumed was 40 minutes. Therefore means that T half is equal to 40 minutes. Okay, I think these were the basic informations that were given. And then now the first question was, we're asked to find the initial speed. Find the initial speed of the reaction. Okay, so that is even what I began with in this video. Initial speed, I said initial speed of the reaction is just the rate of the reaction initially. So the initial speed of a reaction is a reaction rate. So our initial speed is equal to the reaction rate initially, which is just K times the concentration of our reactants raised to its partial order. In this case, the partial order is the total order, which is 2, because we are told that it is a second order alkaline hydrolysis. So this is going to give us K times the initial concentration is 0.01, all that squared. So all we need now is to find the rate constant. Okay, and how then do we find the rate constant? We are going to use what we have had here that concerns second order reactions. We have had this. Okay, so our rate constant normally here, in fact, we had that it was -C. So let us now analyze critically. First, initial concentration is 0.01 molar, meaning that we can say at T equal to 0, we have that the concentration of our reactants, which is ethanoic acid, is equal to 0.01. Now from there, it means we have 1 divided by, I replace this concentration with 0.01, I equate to K times T, which is 0, then minus C. From there, what do I get? I get that minus C is just 1 divided by 0.01, which is 100. So I'm just going to replace 100 here, the minus C here, with positive 100. Okay, so from there now, we get a new equation, since you have used that to find the rate, the constant of integration. So here is plus 100. Okay, now we have to find K. Okay, and what do we say? We said that our T half is equal to 40 minutes. If it was first order, we can find K by taking ln 2 divided by T half, but in this case it is not like that, because it is second order. So we now analyze again. How do we analyze? When T is equal to 40 minutes, that's when the time is 40 minutes, the concentration of ethanoic acid is actually its initial concentration divided by 2, because after 40 minutes half of that was consumed. So the concentration of it at 40 is equal to its initial concentration divided by 2. Okay. Alright, so if I take 0.01 and I divide it by 2 molar. Alright, so from there now, I'm not going to complete the equation. I don't have a calculator close to me. So all you need to do is that you need to now come back to this equation. You replace your concentration here with 0.01 divided by 2. You replace T here with 40 minutes. Just allow your answer in per minute at the end of the day, in minutes even. And then now you find K. So you have 1 divided by 0.01 divided by 2. You subtract 100 and then you divide it by 40. You're going to get K. If you do it correctly, I think I did it and I had K to be 2.5 units. I don't know the units. 2.5 units. From there now, you just need to come back to your and replace K here with 2.5. Okay, and you multiply. I think you're going to get 2.5 times 10 raised to the power -4 units. I've forgotten the units. Okay, now I'm going to leave you guys to do the second exercise, which is saying that we should find the time taken what was the question again? Find the time taken to consume 90% of the reactant. So the time taken to consume 90% of the reactant, yes, something like that. So I'm going to leave you guys to solve and give your answers in the comment section. If you cannot solve, I solved, my answer was 360 minutes. Okay, so if you need hints about that, just indicate in the comment section. Okay guys, thank you for watching this video, and see you in the next video. I don't even know if this video was if the video is not visible, please increase your resolution. Yes, your YouTube resolution, increase it to maybe to 360 or 720 so you can easily see the video clearly. You could also maybe watch this on a full screen, because I was typing, so you might not, maybe the writings might be small, I don't know. So it's preferable and it's advisable to watch it on a full screen so you're able to see everything that was typing. Alright, thank you for sharing the video.